Let's take a look at step 2 of related rates, which is to convert words to variables. Remember, step 1 was drawing a labeled picture. We're going to take that and kind of transition into some mathematical notation. In other words, we're going to take this visual and get a little bit more abstract, going to the mathematical side of things. So what does it mean to convert words to variables? Well, a lot of it is going to be going back to the original question. So here was our original question involving, for example 1, involving water flowing into a tank and asking how fast the water level is rising. And again, it's important to underline this stuff as you read through it. Water pours into a tank. Well, that involves volume. So that's going to give us a good hint as to what variable we should use to represent the water pouring into the fish tank. A rate of 0.3 meters per cube per minute. Okay, so that's a rate is velocity, right, or speed. So keep that in mind. Okay, remember what speed and velocity means in relation to the derivative. It is the derivative, right? So we know this is going to involve the derivative somehow. So there's the next thing. Okay, how fast? Again, that's also the derivative. Is the water level rising? So the rate at which the water level is rising, and that involves height. If the base of the tank is a rectangle of dimensions and 2 by 3. So just kind of make some notes, mental notes, as you read through. What kind of things are you going to be writing out? What are you trying to solve for? Before we go ahead and label these things. So without further ado, let's talk about what each of these things mean. Now we're going to label H the water level height. So there's our first variable, and that's easy because again, the height of this tank doesn't matter. The rate at which it's rising is going to stay the same. What we're ultimately worried about is the rate at which the water level is rising. So we'll label the height of the water H. Okay, now you might be thinking, well, why are we labeling the height if we're worried about the rate at which it's rising? Well, that leads us to our next variable, dH dt. That's going to give us how fast the water level is rising. Now, why is that? Well, we've looked at implicit differentiation, and in general, you should know by now what this notation means. Dy dx means change in y with respect to x. dH dt means change in height with respect to time. So this right here is how fast the water level is rising. Change in height over change in time. Remember that speed or velocity is just distance over time, and that's what we have. It's a rate, it's a fraction, change in height on top, change in time on the bottom. And we can see this is the derivative of h with respect to time. So this is why we need to label the water level height as h. That way, basically, for every variable in a related rates problem, it will have a derivative notation. Now, sometimes that notation might be 0. Like in this case, we could label the length of this 3, right? But dl dt, the rate at which the length of this tank is changing, is 0, because the water will always have a length of 3 meters, regardless of how far it's going up. The same for the width. But at any rate, you can write that down if you want. Just know that it's going to be 0. Next, V, the volume of water. Again, it involves volume, so we're going to use V for volume. And again, that volume is changing, okay? dV dt is the rate at which the water would be pouring in. Change in volume with respect to change in time. We already know what that is. It is 0.3 meters cubed per minute. So we could, assign that value, dV dt equals 3. Just a few more things. You can label, not all of these are as important as others, but like I said, it's important to be thorough. We'll go ahead and call the length of the tank L and the width of the tank W. As far as I know, that's about as thorough as it gets. Okay. Again, you could say dl dt and dw dt, but those are just zero. I don't mind if you do that, but for this particular problem, it won't matter. So that's it for step 2. For example 1, again, we're just going to do one step at a time. In this case, we're just converting words to variables. And, this one is a little bit harder than drawing a picture, but I think as long as you understand the notation of calculus and kind of, the dHdt and the dVdt just mean the rate at which something is changing, whatever it's changing, then that's going to really help you assigning these variables to the different words in the problem. Here was our example 2 of a ladder sliding away from a wall. And, we ultimately want to know the rate at which the height of the ladder is falling. Maybe by now you can see that's going to be what? dHdt, right? It's the rate, the change in height over the change in time. Okay, so for step 2 for this one, we're going to call h the height of the top of the ladder. Again, for every rate, you need a variable assigned associated with that rate and vice versa. So since the variable is h, the velocity would be dHdt. Now, since it's falling, you can pretty much tell, it's going to have a negative velocity. If you think of it, depends on your point of reference, actually. Since it's going towards the ground, you could also say it's positive. It doesn't really matter. It depends on your reference point. But anyways, it is falling. So dHdt, though, is going to represent the change in height over change in time at the top of the ladder. X, now you could say D for this, doesn't matter, but we have ddt, so I just used X. X is going to be the distance from the bottom of the ladder to the wall. So X will be this distance, and you can see it's changing as the ladder slides away from the wall. The distance it goes away, X, is going to increase. By the time it falls all the way down, X will be 5. The bottom of the ladder will be 5 feet or meters, whatever we said, 5 meters away from the wall. So X changes, and therefore we're going to label dx dt the velocity of the bottom of the ladder. And it's going to, of course, change as the ladder falls. Or actually, I'm sorry, it stays the same. It's 0.8 meters per second. Falls at a constant rate of 1.5 meters from the wall. Oh, I'm sorry, 0.8. Sorry, I misspoke. Slides away from the wall at a rate of 0.8 meters per second. So that's important. No matter when this ladder is sliding, it's always going to be sliding at that rate. Even at the end, it's going to be going 0.8 meters per second away from the wall. Started out at 1.5 meters from the wall. So that means dx dt, the rate, what's the distance from the bottom of the ladder to the wall is changing, is going to be the velocity. Okay, so that's actually it for this example. Those are all the variables we need. We have an h, dHdt, an x, and a dxdt. You can use different notation, actually. I didn't really mention that. Remember, another way to talk about the derivative of h, for example, would be h prime. So h prime would be the same as dh dt. And then, dx dt you could write as x prime. But I find that the fractional notation works a little bit better with related rates. What can do whatever you like, though, in regards to that. Okay, let's look at example 3. We had a conical tank going down into water going into it, and we were basically trying to figure out how fast, at what rate is the water level rising when the water level is 5 meters high. We have a lot of variables here. I'm going to try to talk about each one of these best I know how. We have a height of the water, we have the radius of the water, we have a lot going on. Since we're trying to solve for the rate at which the water level is rising, let's go ahead for step 2 and we convert words to variables. Let's call h the water level height. Then we're going to call dHdt the rate of increase of water level height. Okay, and we know it's going up, and since the derivative of h is dHdt, that will give us the rate of increase of water level height. How fast is this rising? All right, next, r is the radius of the water surface. This will be changing, right? We talked about the fact if you fill this water completely up, the radius will be 4. Down here at the very bottom, it's going to be just a few centimeters, right? In fact, if you just put 1 drop of water in here, the radius of that water would be practically 0, right? So you can see as the water fills up, the radius is going to change. Therefore, we are going to have a dr dt, the rate at which the radius is changing of the water surface. Okay, lastly, the volume of water we're going to call V naturally. We can see the volume will be increasing as well as it fills up. And dV dt is going to be the change in the volume of water. Okay? So here's the thing, conceptually, since it's coming in at a rate of 6 meters cubed per minute, it's going to be increasing at the same rate. No matter the shape of your tank, if it's coming in as a constant rate, the volume is going to be increasing at the same rate. Now, the volume is going to be different as it goes up, right? But the rate at which it's increasing is still 6 meters cubed per minute. So that means one minute later, no matter what, it's going to have 6 cubic meters more of water in here. Okay? Now, why do we focus on V? Because they gave us the rate at which it's coming in, so it's important we know V. And if you think about the formula for the volume of a cone, it involves, was it 1/3 pi r squared h? So we need V, R, and H. You need all those variables because the formula involves all 3. Okay, so we basically used all these figures to come up with variables for each of these things. Okay, so there's your variables for this example. Again, we're just doing one step at a time. Right now we're going to focus on example 2, which is converting words to variables. And I just think that if you do focus on these problems and just do one step at a time, you're going to have a lot more success at first rather than trying to do all steps at once. Now, eventually, of course, you'll get to the point where you can do all steps at one time, no problem, right? But learning it one step at a time, I think, really breaks it down step by step to make it seem a little bit more manageable. That sometimes it can be really overwhelming if at first you try to do all steps at once. It's better to learn one step at a time, just like walking or learning basketball. You learn to dribble, then you learn to, do a layup, and then maybe a foul shot and that kind of thing. So here was our last example of coffee draining from a conical filter into a cylindrical coffee pot. I'm going to go ahead and get right into this one. This is going to be our most involved one because we have 2 different shapes. We have different rates. So for our step 2, when we convert words to variables, we're going to label label the radius of the coffee in the filter as radius 1. So this is radius 1. It's going to decrease as the coffee drips into the pot. Okay. And again, this is dropping at a rate of 1 inch per minute. So naturally the radius is going to go down as it falls down. So it's important that because we have different radius or radii. And then the rate at which that is changing is going to be dr1 dt. So, every time you have a measurement, just go ahead and write out its derivative. Even if that derivative is 0, you might as well just go ahead and convert those words to variables. Like I said, just be thorough. Then we're going to have the height of the coffee in this filter. We're going to call it h1. And then the rate in which that height is changing is dh1 dt. And then we're going to have V1, which is the volume of coffee in the filter, and dV1 dt, the rate of change of that volume. Obviously, it's going to go down as this drops. Now, you might be saying, how do I know I've got all my variables? Okay, well, think about this shape, a cone. Okay, what do you need to know about a cone to know its volume? You need to know its radius, its height, and that's it, 1/3 pi r squared h, right? And that gives you the volume. That's 3 variables, V, H, and R. So we've covered every variable for the volume and we wrote out its derivative. Since this is a related rates problem, once you've got the derivative variables written out, you're good to go, okay? You've got the 3 measurements and the 3 variables. So that being said, let's take a look at the cylinder. What do you need to know for a cylinder to know its volume? You need to know its radius, right? And you need to know the height. And what's the formula for the volume of the cylinder? It's basically the area of the bottom, the base, which is pi r squared, and then times height. So what variable? Pi is in the variable. Variables are r and h. And that gives you v. So another 3 variables down here. So I'm going to call I said d2 for the diameter. You just need to know the radius. The radius of the cylinder I'm going to call r2. The rate at which it's changing I'm going to call it dr2 dt. Now again, it won't change at all. Okay, it's going to remain constant. So it's going to be 0. But like I said, just be thorough. Especially when you first start out, you don't know. I remember when I first started doing these, I was like, well, what variables do I need to know? What do I not need to know? Well, just write everything out. That way, as you solve the problem, you have everything you need. It's kind of like going to the lumber store, and you might think, well, do I need this or do I not? Well, if you're going to do a job, you might as well buy everything, right? That way, when you get to the job, if you don't need it, you can always just take it back, right? Same kind of thing here. Next, we're going to label the height of the pot, H2, since we labeled the height of the cone H1. The rate at which is changing is dH2 dt. Now again, now this one will be changing because the water is rising in the pot, and that's actually what we're trying to solve. How fast is the level of the coffee pot rising? So we're trying to find dH2 dt, the rate at which the coffee is rising. Finally, V2, the volume of coffee in the pot. And then dV2 dt is going to be the rate at which that is increasing, and that's also going to be changing. So basically for these rates, the only one's constant is the rate at which the radius is changing. It's 0. Okay? Or I should say that's the only one that's 0. These other rates might be constant. I just know they're not going to be 0. They're going to be, this one's going to be increasing, and height is going to be increasing in the cylindrical pot. So that's it. Those are our variables for our 4th one. Again, this is by far the most involved as far as converting words to variables. This step is really important because, like I said, it's kind of like a bridge between, taking this really kind of abstract sentence, drawing a picture, and then writing out what your variables are, because from this point you can jump full on into the math. Start to write your formula out, plug some stuff in, take the derivative, and solve the problem. Again, for this one, you're trying to solve the rate at which this coffee is rising when there's 5 inches of coffee in here and it's falling at a rate of 1 inch per minute. How fast is this rising? Is it rising 2 inches per minute? 1.5 inches per minute? I don't know, but we're one step closer to getting there. That's it for step 2 of converting words to variables for related rates problems. If you have any other questions about this, let me know.